Hi everyone. In my PhD project, I'm investigating the role of artificial intelligence in decision-making for extubation of mechanically ventilated patients. We were told that the introduction should be dramatic, so let me kick off with the striking fact that nearly every second ICU patient requires mechanical ventilation, yet no consistent guideline exists on when to extubate these patients successfully. Machine learning shows promise in clinical outcome prediction, but its predictive performance on extubation success remains unclear. Our systematic review and meta-analysis shows that machine learning models are able to predict extubation success with up to 90% of accuracy. Our results suggest that these models should form an integral part of future weaning strategies, while further clinical prospective studies are needed to standardize and validate machine learning-based predictive models. Also, policymakers should support the development and the integration of AI tools to optimize extubation timing and also ICU patient outcomes. I'm Péter Bakos, an anesthesiologist and intensive care physician working in West Prim at the Department of Anesthesiology and Intensive Care. My vision is healthcare professionals at the bedside relying on data instead of customs and traditions, while my mission is to provide evidence on data-driven decision-making in critical care. Last year, we set specific goals. First, we are investigating the accuracy of already existing machine learning models in predicting extubation success. And then in a second step, based on the findings and results of the first study, we are planning to develop and validate a clinically applicable machine learning model. So let's start with the first project and its background. The most important problem related to the topic is that almost half of our ICU patients are mechanically ventilated. There are existing national and local protocols on extubation, but despite these protocols, the intubation rate remains quite high, between 10 and 20%. Also, the practice on extubation varies widely among ICU centers and physicians, leading to inconsistencies. So what do we know so far? We know that even failed or delayed extubation may cause complications and affect outcomes such as ventilator-free days, length of stay in ICU, or increased mortality. Also, it has been already shown in previous publications that machine learning can predict outcomes such as mortality or renal failure. So what is really missing is consistent guidelines related to the topic and evidence certifying the predictive accuracy of ML on extubation success. So what we can do for that is investigating the performance of machine learning predictive models. Our clinical question in this study is whether machine learning models are superior to standard medical therapy in predicting extubation success in mechanically ventilated patients. To answer this question, we use the PIRD diagnostic framework, where population is mechanically ventilated patients undergoing extubation. Index test 1 is ML models, index test 2 is standard medical therapy, reference is extubation success, while D is prediction accuracy. Our hypothesis is that machine learning models are superior to standard medical therapy in predicting extubation success. So having these kind of tools in clinical practice could actually first improve our patients' outcomes, second, decrease the burden on healthcare professionals, and third, enhance cost effectiveness. The clinical and research implication of this study would be the use of ML models as part of standard of care. We conducted a systematic search in 3 different databases. Our search key consists of 2 domains. Domain 1 refers to the population of the study, while domain 2 to the predictive algorithms and machine learning models. As you can see, we had more than 13,000 results, and we performed duplicate removal, also title and abstract selection, full text selection. Finally, we had 26 eligible articles for this review. Here you can see our main results. Again, our population was mechanically ventilated patients undergoing extubation. On the left, you can see the eligible articles with the best performing machine learning models and with the sample size of the studies. And the outcome measure was area under the curve, AUC, which is the most frequently presented outcome measure in diagnostic test studies. And AUC has no unit of measure. Its values range between 0 and 1. So numbers close to 1 means very good predictive performance, while numbers close to 0.5 mean actually random classification. And what you can see here is that the pooled AUC of the best performing models in this study was 0.90. We also performed subgroup analysis, and here you can see the largest categories of machine learning models. And what you can see is that the most advanced technologies, deep learning models, had a similar predictive performance compared to the classical or traditional machine learning models with a pooled AUC of above 0.85. On the other hand, the most frequently presented clinical index, which is rapid shallow breathing index, it had a pooled AUC of 0.57 only. Of course, our study has strengths and limitations. Among strengths, we can mention that our results are coherent. We could identify several subgroups, and also we applied a comparative context. On the other hand, most of the studies were based on retrospective data, and the heterogeneity was very high due to the different types of models and predictors applied. And also external validation was limited in these studies. So in conclusion, we can say that machine learning models can accurately predict extubation success. The implication for practice would be that machine learning models should form an integral part of future winning strategies, while implication for research is prospective clinical trials are needed to standardize and validate ML models in the future. Currently, we are writing the first draft of the manuscript, and hopefully we can send it to internal review next month. So let's move to the second project, which is a development and validation of a clinically applicable machine learning model that applies clinically relevant predictors. So building a machine learning model consists of several steps. First, we need to start with idea conceptualization. That means we need to define the features or predictors and the outcomes we are planning to use, such as extubation success in our case. The second step is data collection. Actually, this step could take years or even decades. For that reason, we are planning to use already existing, well-structured open source ICU datasets. Third step is tool identification. We need to identify define the programming language and the machine learning model type we are planning to use. So at this stage, let's jump to the figure on the right in order to understand the term supervised learning in machine learning. So supervised learning is a type of algorithm that applies predefined features and outcomes. With the help of large labeled ICU datasets, our model is trained to make it able to do predictions and decisions based on new unseen data. Next step is data cleaning. We need to identify missing values, inconsistencies, and outliers in the data set. And then we can build our model, and we should evaluate its performance. So what we have so far is a programming code. We need to implement it in a real-world environment. We need deployment. And of course, once we have our model, we should share it with users, with clinicians, in order to rely on their feedback to improve our model further. So in summary, we have two projects ongoing. First, we are investigating the accuracy of already existing machine learning models, and in the second step, we are planning to develop and validate a machine learning model based on the results of the first study. And for the question, when to extubate a patient, the answer, my friend, is blowing in the wind. It's in the data, but we need to find it. Thank you very much for your attention.
Thank you. Congrats, Patty, for the third time for your nice presentation. In your first project, you mentioned the limitation with the low external validation. What does that mean in this process, the external validation?
External validation means that when you train and test a model, you use a data set, an ICU data set. But it's very important to validate it on another completely different data set in order to make sure that there is no bias. And, but it's not always possible, and how to say, the source of these data sets is limited, and not every study could perform external validation. But in the future, it's very important to have it, because if your model is working only on one given ICU data set, you are not sure that it's working in any other setting. So that's why it's needed.
Yeah, I understand. Thank you.
Thank you for your nice presentation.
Thank you.
Are these data sets hackable at all? Or like this machine, like, no, but like...
What do you mean hackable?
Like, if you're teaching it, right, based on all of these data sets, but if somebody hacks into it and like ruins all of the data sets, like, is there like a cybersecurity situation?
Actually, I hope that they are not hackable. So these are very strictly provided the data sets, and you can have you should fulfill a course to be able to have access to it. You have to be an intensivist, and you have to have the right to use these data sets. So it's not freely available to everyone, but for the ones who are interested in it and who are qualified to use it.
Thank you.
Okay, so my question would be, my concern is that these machine learning systems and AI working with a proper data set, and it's a good question, I think, how would you give the data for the system? Do the system measure it itself, like the ventilatory parameters, or you need to give the parameters from your own perspective, like muscle weakness, or the consistency, or the amount of tracheal secretion is also really important, and it's hard to measure?
Yes, that was one of the aims of our study, to see which are the most important predictors or features. That means that in one study they used, for example, only the ventilatory parameters. Other studies included also comorbidities or hemodynamic parameters, or even diagnostic tests. And that's very important to, I think, in the future, because most of these studies are not applicable now clinically. So the point is to have a clinically relevant and applicable application, actually, to be able to give the parameters you are interested in, and then the machine can support your decision on extubation. So that's the point.
And what do you think, how accurate can the system suggest the extubation time? So hopefully will there be no reintubation in the future?
There will be, I'm pretty sure. So there are studies that are focusing on the timing on extubation. Currently, in this study, we were focusing on the outcome, on the prediction of the outcome. But also, as I said in the background, that even the delay of extubation can cause harm to the patient, very severe harm. And it's very heterogeneous how centers and ICU physicians extubate a patient. So someone would extubate a patient on day 2, the other one would extubate on day 4, and that's a big difference. And that's why first we should have protocols and consistent guidelines, and then probably we need these machine learning models to support our decisions, because we are not able to integrate all these parameters, because there are models that use, for example, 89 parameters, but as a human being we are not able to do it. I think so.